Hello. The purpose of this video is to review for you how to use electron dot notation to represent or model ionic bonding. Let's get started. You will be given two elements, a metal, such as potassium, and a nonmetal, such as bromine. The first step in doing electron dot notation is to write those chemical symbols down on the paper, leaving yourself enough room to work. As we talked about in class, these chemical symbols represent the nucleus of those atoms and the inner electrons, the electrons that will not be involved in the bonding. That's what that K represents. That's what that Br represents. What will be involved in bonding are the outer electrons, are the valence electrons of each atom. How do we know how many valence electrons potassium has? We go to the periodic table and we find potassium. It's in the first column and the fourth row with an atomic number of 19. As I look in the potassium block on the periodic table, in the upper right-hand corner, I see the electron configuration for potassium is argon 4s1. What does that mean? It means that the inner electrons are configured exactly like argon. Argon, as you can see, is in the 18th column. It's a noble gas. It's not reactive. It's stable. Those electrons will not be reacting. There's only one electron in the highest occupied level for potassium. Potassium is on the fourth row of the periodic table. The highest N energy level for its electrons is the fourth level, and there's only one electron there. That's the valence electron of potassium. Similarly, for bromine, I go across the table to column 17, still in row 4, atomic number 35. Bromine also has that inner configuration of argon, and on top of that, for valence electrons, it has 2 in the s orbital, and it has 5 in the p orbitals. That s orbital and those p orbitals are all on the fourth main energy level. So the highest occupied energy level for bromine is the fourth level, which corresponds to the row that it's found in on the periodic table. Fourth level, 2 in the s plus 5 in the p's, 7 valence electrons for bromine. Those are the electrons that are available for bonding. So my next step in doing electron dot notation is to represent those valence electrons. Potassium has 1, and bromine has 7. I like to use X's and O's so I can tell who has what and where things came from. Not everybody does it that way. The main thing is to have some sort of symbol around the letters, and the number of the symbols corresponds to the number of valence electrons. Potassium has 1, bromine has 7. As we talked about in class, 8 is great. We are going for that noble gas configuration, that octet of 8 electrons. Well, potassium is 7 away from 8. That's a long way, relatively speaking. That would take a lot of energy. So it's easier for potassium energetically to simply lose 1 electron. Conversely, bromine has 7 valence electrons. It's only 1 away from an octet. This is rather convenient. Potassium is going to lose its 1 electron. It's 100% giving it up to bromine. And bromine is 100% taking it on. Does that mean potassium no longer has any electrons? No, that K represents all the inner electrons along with the nucleus. So what have we got now? we have 19 protons, because potassium has an atomic number of 19. It had 19 electrons, but it just gave one up to bromine, so now it has 18 electrons. Each proton has a positive 1 charge. 19 protons yields a total positive charge of 19. There's 18 electrons. Each electron has a negative 1 charge. If there's 18 electrons and each has a negative 1 charge, there's a total negative charge of 18. Positive 19 plus negative 18 yields an overall charge of positive 1 on that potassium. Let's go to bromine. It started with 35 protons. How do I know that? The blue number next to bromine in the periodic table is 35. That's the atomic number, the number of protons. And it started with 35 electrons. But it just gained 1 from potassium. So now it has 36 electrons. 35 protons means we have a positive 35 charge on the nucleus. 36 electrons means that we have a negative 36 charge in the electron clouds. Positive 35 plus negative 36 yields an overall charge of negative 1 on the bromine. They started off as neutral atoms, but now they have charges. Atoms that have charges are called ions. So this is now a potassium ion. This is now a bromide ion. Positive ions are called cations because cats are better than dogs. Just kidding. Negative ions are called anions. And as you know, opposites attract. So the positive cations are attracted to the negative anions. And they come together in an ionic bond to make this compound, potassium bromide. Notice that the charge on the potassium plus the charge on the bromide equals 0. The overall charge on ionic compounds is 0. So all the positive charges added to all the negative charges must always equal 0 for a correct ionic formula. This is the correct ionic formula for how potassium and bromine combine together. There's 1 potassium for every 1 bromide. But in chemistry, we don't write the ones. We only write if there's more than 1. So this is the correct formula for potassium bromide. When you do these problems for me to turn in or on a test, these are the things that I need to see. Number 1, the chemical symbols. In this case, it's the K and the Br. That's what I mean by chemical symbols. Second, show the valence electrons on each atom. Third, you need to draw arrows showing the movement of the electrons. Fourth, the overall charge. The overall charges. All the atoms need to have an overall charge on them. And 5, the correct formula. In the correct formula, the cation, the metal, always comes first. And the anion always comes second. So we would not write this BRK. We would always write it KBr. Let's do another example. One that's not in a 1-to-1 ratio. Let's take magnesium and nitrogen. Step number 1, write the chemical symbols, Mg and N. Step number 2, put valence electrons around each of the atoms. Magnesium has 2, nitrogen has 5. You get those numbers from the periodic table. Get these out of the way. Next, arrows to show movement of electrons. Well, this is going to come here. This is going to come here. The overall charge now on magnesium is +2 because it lost 2 negative electrons. It's satisfied. It has a complete octet now left around it. But nitrogen is still 1 short. There needs to be another magnesium in this situation. And it'll have another 2 valence electrons. And one of those valence electrons is going to move up here to give the nitrogen an octet. Oh no! The second magnesium is not satisfied. So I need another nitrogen. And it'll have another 5 electrons around it. So now this magnesium can give this electron to this other nitrogen. And now this magnesium is satisfied. It has a +2 charge. It lost its 2 valence electrons. But our nitrogen's short, so we need another magnesium with another 2 electrons. And now this third magnesium can give up those 2 electrons to satisfy this nitrogen. We're done, because now all the magnesiums have the octets of their inner electrons on the outside. Both of the nitrogens have filled their valence level. Because each nitrogen gained 3 negative electrons, they each have a -3 charge. So now I have satisfied number 4 with overall charges. I have them on each of the atoms in my diagram. The correct formula will have 1, 2, 3 magnesiums, Mg3, and 1, 2 nitrogens, N2. This is the correct formula for magnesium nitride. I hope this helps.